Welcome to Calc Chats 20. Today we're going to be diving into anti-differentiation techniques when we talk about the definite integral and the indefinite integral. We've already discussed what a definite integral is. It's the area under a curve, and it is usually between, always between 2 points. And the way we write a definite integral looks something like the integral from a to b of f of x dx. That's our general notation for a definite integral. For an indefinite integral, that's where we don't really have a bound, but we're just kind of trying to possibly see what the area under this curve is. So we generally write this no bounds, just the integral of f of x dx. And so far we've solved definite integrals with geometric formulas. That was when we would take the area of the circle and add it to the area of the triangle, that kind of stuff. And Riemann sums, left, right, midpoint, and trapezoidal. We've even used our calculators to solve some, and we've used those integral properties when they kind of give us f, the integral of f of x is 2, the integral of g of x is 5. So we've used a lot of different ways so far. But now we're kind of going to get into a new way, which is called anti-differentiation. And so this is something that we're going to use to solve definite and indefinite integrals, and it's kind of like our backwards derivative. So instead of taking the derivative, we take the antiderivative. So our first example is if we're just going to look at the integral of cosine x dx. And this is an indefinite integral. My bounds aren't defined. So if I think about the opposite derivative, the backwards derivative, I know that the derivative of sine x is cosine x, and so the integral of cosine x is actually sine x. So these trig identities are a little tricky to get used to, but again, we're just going backwards. So if you know that the derivative of sine is cosine, that means the antiderivative of cosine is sine. And another thing that we have to do when we take indefinite integrals is use this plus c. And so when we take the derivative of something, if we took the derivative of sine x plus 2, whenever I take that derivative, this just becomes cosine x. This goes to 0. And so when I add in that plus c, and we're going to be solving for this later, but when I add in that plus c, that's just taking into account that my graph could look like this, or it could look like, it could be, that's not a very good example because that's not even sine. All right, it could look like this, or it could be further up, look like this. So that's just accounting for that possibility that something was taken out when they took the derivative. So that's kind of trig. Trig is just the opposite derivative. Now we're going to kind of get into the reverse power rules, what I call it. So the integral of x squared dx. So what we do to solve these types of integrals is when we take the derivative, we subtract 1. So when we take the integral, we add 1 to the exponent. And when we took the derivative, we multiplied by the new exponent, and now we're going to divide by the new exponent. So the integral of x squared is x cubed over 3 plus c. And again, please remember that plus c. That is very important when we have indefinite integrals. And if I wanted to take the derivative, just to double check, so the derivative of x cubed over 3, bring the 3 down, subtract 1, we get x squared. So we're good to go. So for E and Ln, they're very similar to our reverse power rule. And so e to the mx dx, m is a constant. When we take the derivative of e to the mx, we just bring down that m and we keep e to the mx. And so when we take the integral, we're, again, just going to divide by that constant. So e to the mx plus c. So this is kind of our basis for integrating e. And it's important to remember that that m is a constant. So I can't have x squared up here. I can't have x cubed or like sine times x. I need to have just m as a constant. And for ln, when we take that integral 1 over x, we need to have an absolute value when we take that integral. So these are kind of our rules for e and ln. E is pretty simple. Just when integrating, we have to just be careful that we have the absolute value bars. So we are in calculus, and so we are going to talk about more theorems of calculus. And this is called the fundamental theorem of calculus, and this is kind of the evaluation part. So if I'm given a function f and it's continuous on the closed interval, and I define this big F as the antiderivative, then the definite integral from a to b of f of x dx is equal to the antiderivative of b minus the antiderivative of a. And if I kind of think about this in terms of area, if I'm given a curve and I want to say go from 0 to, no, let's not say 0, let's say 1 to 3. Well, if I take all the area from 0 up to 1, that's this green part, that's f of a. And if I take the area all the way up to 3, that's f of b. And so when I subtract them together, when I subtract f of b minus f of a, I take out that part between 0 and 1. And so then all I'm left with is the stuff in blue. So this is a very basic kind of understanding of what's going on with this f of a minus f of b. But once I find the antiderivative, all I have to do is subtract. Well, I have to evaluate those terms and then subtract them, and then I'm good. I can find the area. So some examples of this. So -1 to 3, x cubed plus 1 dx. So first thing I need to do is I'm going to try to evaluate this integral. And I need to find the antiderivative first. So I'm just going to use my power rules for x cubed. So this becomes x to the 4th over 4. And then the integral of 1, this is technically x to the 0 power. So I add 1 and divide by 1. And so I actually just get x. And then here, my bounds, -1 to 3. This is how we write it when we are evaluating. So this is just, these brackets are just notations. But this represents our antiderivative. And then these two numbers represent our bounds. So now I have my antiderivative, I have my bounds. So now I'm going to plug them in. So I'm going to take, let's go back up a little bit. So I'm going to take 3 to the 4th over 4 plus 3, and then I'm going to subtract all of this, -1 to the 4th over 4 plus -1. And this is something that I could quick plug in my calculator to evaluate, but I should get 24. So the definite integral from -1 to 3 is 24. Another example is if we take the integral from 0 to pi of 1 plus cosine x dx. And so first I need to find the antiderivative. So the antiderivative of 1 is x, and the antiderivative of cosine is sine x. So then I'm going to evaluate that from 0 to pi. So I'm going to plug in pi wherever I see x. So pi plus sine of pi minus 0 plus sine of 0. And this ends up just being pi. So that's the last problem I have to work through with you guys. I have a few DIY problems, so I am just going to kind of scroll down and show you the 2 problems, and then I'm going to pause, do the work, and if you want to try them on your own and then check your answers, that's great. If you don't want to, you can stop the video now. Just make sure to like and subscribe. But these are our 2 problems. So the integral of 0 to 4, 1 minus root u over root u, and then negative 2 to 1, 2 over x squared dx. So I'm going to give you a second to write these down. I'm going to pause it and show the complete solution. So here we have the first solution. You should have gotten 5/3. And then our second solution, you should have gotten 1. So this is kind of the beginnings to antiderivatives. We're going to learn a lot more of different ways to find integrals and find antiderivatives. And we're also going to compile a list of all these rules because trig identities, those can be hard. So please like and subscribe, come to class with any questions, and make sure to keep on watching Calc Chats with Miss R.